Hello and welcome to Nurture Academy. Today we are going to do some numericals based upon dual nature of matter. This unit is there in plus 2 physics volume 2. Now when we are talking about dual nature is a unexplained phenomena without talking about de Broglie relation. Suppose this is the de Broglie relation. Alpha is equal to h upon p, where p is the momentum of the particle, which is in turn equal to m into v. For solving any given numerical, number one, we should know de Broglie relation. Second thing, what is important for us to know is what is the relation between momentum and kinetic energy. So this is actually a very classic thing in physics. We know that kinetic energy is equal to half mv square and momentum is equal to m multiplied by v. How about if I want to find relation between two things which are looking similar but not exactly similar? So how about I multiply kinetic energy by m and divide by m. So if I do that, then I am going to get the relation rewritten as half m square v square divided by 2 times m. Now notice here that momentum was nothing but m into v. So here instead of m square v square, we will write p square and we are going to get the relation kinetic energy is nothing but p square divided by 2m. Doesn't stop here. One, this relation you have to remember. One, as I said, de Broglie relation. Now connect the value of P from here. Instead of P, we are going to convert it in terms of lambda. So we can say kinetic energy is equal to h square upon lambda square into 2m, right? That will be your kinetic energy. Now if I rearrange, I can technically find the value of lambda. Lambda will be written as under root of h square upon 2m kinetic energy. Sometimes what happens in many numericals, instead of giving you kinetic energy, they will give not in joules, they will give the value in electron volt. Okay, so we have to be prepared to solve all these numericals. Just keep these formulas in mind to start with the simple numericals. Lambda is equal to h by p. Kinetic energy is p square by 2m and lambda is equal to under root of. So for the next few numericals, we are going to remember this particular relation. Lambda is equal to h upon root of 2m into E into V, where E is the charge on each and every electron and V is the potential. Now let's move on to the given question. We are given an electron and alpha particle. Whenever we are doing any comparison type question, here you say electron, here you say alpha particle. They have same de Broglie wavelength associated with them. So we can say here lambda into E is equal to lambda into alpha. That's what we can tell. And next they are asking, calculate how their kinetic energies will be related to each other. So, now we already know the relation between kinetic energy and lambda. Since lambda for both of them is same, we can just compare them. H is constant. Mass, by mass, we will rearrange this equation. 2 is also a constant. So basically we will get 1 upon root of mass of electron. That should be equal to 1 upon root of mass of alpha particle. And of course, this side we have kinetic energy of electron and this side we have kinetic energy of alpha particle. Again, if you cross multiply this equation, you take m alpha here and you take me here. So we know very clearly that mass of alpha particle is much more as compared to mass of electron. When you see the ratio, then you will clearly know that kinetic energy of the electron in this case will be more than the kinetic energy of the alpha particle. So by using this relation, we can solve this numerical easily. So in this given question, again, we are using the same formula. Remember, lambda is equal to h upon root of 2m e into v. In this question, they told that there are two lines A and B, and the plot is between lambda versus 1 by v. Lambda means wavelength and 1 by v means that 1 upon potential. And we have to figure out that out of A and B, which particle has the smaller mass. So actually this graph is very simple. You compare it to the formula lambda and 1 by root V. Okay, so if you're plotting a graph between lambda and root V, right? So you are left only with the factor root 2 and mass of electron. Mass of electron is a constant, 2 is a constant. So basically, the slope will give you the value of mass. And as you can see, lambda is inversely proportional to mass. Inversely proportional means lambda is in numerator and root of mass is in denominator. That means that whichever line has more slope will have lesser mass, because formula of slope is y is equal to mx plus c. C is not there. In this case, value on y-axis is lambda, value of x-axis is 1 by v. So slope is giving you the value of 1 by root of m. That is the slope. Hence, using this formula, B has small mass. This is very simple math. Let's try one more numerical based upon the same formula. So here is one more numerical based upon the same de Broglie relation relating kinetic energy to momentum. In this numerical, we are asked to plot a graph between lambda and potential. Remember, in the previous numerical, we were making the graph between lambda and 1 by v. The graph was given, that's why it was straight line. But if you notice, by this relation, lambda is actually inversely proportional to root of v. That is why when you plot the graph, it will be a exponentially decreasing slope graph. Let's move on to the next variety of questions which are asked in dual nature of matter. So next variety is basically called photoelectric effect. When a photon of light falls onto the metal surface, then electrons are ejected. This is the mathematical expression for photoelectric effect. 2 points which we have to remember. Energy of the photoelectron depends upon frequency and not on intensity. Once we have threshold frequency, if you increase intensity, photocurrent is going to increase. Now, in this particular question, they are asking that you are given a variation of photocurrent. This is photocurrent versus the stopping potential V. Stopping potential means you know that stopping potential is actually in terms of the kinetic energy of the given photoelectron. You can treat it like energy. So, three things are given, I1, I2 and I3 at three different intensities. What we have to figure out is that which two curves have same frequencies but different intensities. This is the thing we have to figure out. Okay, so let's see the graph very, very carefully. If you notice, this point of origin is same. So at this point, stopping potential for these two curves is same. Here, stopping potential is different. Potential, as I told, is nothing but the kinetic energy. And here we have figured out that energy depend upon frequency. So what does that mean? A and B have same frequency because they have same stopping potential, even though their intensities I2 and I3 are different. This is the important variety of question. Let's try one more to understand it better. Now, this one is one of the very, very, very interesting graph to interpret, again based upon the application of the photoelectric effect. Let's see how do you solve this kind of numericals. So we are being given again the graph between photocurrent and stopping potential. Remember, same thing, energy directly proportional to frequency. Okay, and energy is also in terms of, we can write in terms of volt. Okay, no confusion. And current is actually in terms of intensity. Okay, okay, it happens to be that, both symbol are written by I, but we are plotting a graph between current, and these values are actually intensity, not current. Anyways, so in this given question, they are asking that there are two different photosensitive materials. Okay, we have to figure out the pairs of different materials. Okay, they have same intensity of incident radiation. Okay, for a second, forget same intensity of incident radiation. Let's concentrate on, in these type of graph, how will you figure out whether two different materials are being given? So remember, in chemistry, we always learn that every given element will have something called a ionization energy. Photoelectric effect is nothing but an extended application of ionization energy only. And if you go down the group like lithium, sodium, potassium, rubidium, and cesium, then ionization energy of cesium is least and lithium is maximum. So means that energy in term of frequency and different material will have different ionization energy. So actually it's very simple now to figure out. This is one material and this is another material. Okay, so curve 1 and curve 2 are same material. Same way, curve 3 and curve 4, they are also same material. Why same material? Because they are on the same energy level. But intensity wise, if you notice, then we can see that curve 1 and curve 3 have same intensity, and same way curve 2 and curve 4, they have same intensity of light. Intensity is different than energy. These materials have same intensity, but 1 and 2 are actually same material and 3 and 4 are same material. Let's say this particular graph. This graph is given between stopping potential and frequency. I'm telling you guys again and again, potential is actually in terms of energy. Okay, so energy according to Einstein relation is written by the expression E is equal to H times nu. That means energy is actually directly proportional to frequency. That's why if you see the graph, it's a straight line. All we need to tell is that there are two materials, A and B. Both are metals. you have to tell which one has higher value of energy. So I've already told you that energy is nothing but potential, and potential directly proportional to frequency. All we need to do is we have to check on the frequency axis that which one has higher frequency. So when you notice metal A has higher frequency as compared to metal B. Since its frequency is higher, so its work function will also be automatically higher. So I hope this module will help you in understanding dual nature better. If you guys have any question, you can ask in the comment section. Please like, share, subscribe our channel for many more videos like this. Thank you.